Could our universe have begun in an entirely different way than we are taught? Most people know the basic story of the Big Bang, but that is just one of many competing ideas. We are going to explore 25 controversial theories about how everything began. These are concepts that challenge the foundations of mainstream science and could completely reshape your understanding of reality itself. Some suggest our universe is a simulation, while others propose it has no beginning at all. By the end, you will see the cosmos through a completely new lens. How many of these ideas do you think could be true? The story often starts with a single, cataclysmic event. The Big Bang Theory is the prevailing narrative, the one you likely learned in school. It proposes that our entire universe, all of space, time, and matter, was once compressed into an infinitely dense and hot point called a singularity. Then, approximately 13.8 billion years ago, this singularity began to expand at an incredible rate, birthing the cosmos we see today. We have compelling evidence for this. The universe is still expanding as Edwin Hubble observed galaxies moving away from us, and we can detect the faint afterglow of that primordial fireball, the cosmic microwave background radiation, which fills all of space like a ghostly whisper from the beginning. Yet, for all its strengths, this foundational theory is not without profound mysteries. The equations of the Big Bang work beautifully from a tiny fraction of a second after the event began, but they break down completely at the moment of the singularity itself. Physics as we know it simply stops. This leaves gaping, unanswered questions. What, if anything, caused the bang to happen? What could possibly have existed before space and time began? These are not small oversights. They are fundamental chasms in our understanding, and it is these very gaps that have fueled the search for other, more controversial explanations for our cosmic origin. That very problem, the breakdown of physics at the singularity, is precisely what led some of the 20th century's greatest minds to propose a radically different vision. Before the evidence became overwhelming, the Big Bang had a formidable rival, a theory that painted the cosmos as eternal and unchanging in its broadest view. This was the steady-state theory. It suggested the universe had no beginning and will have no end. There was no explosive origin, no moment of creation. Instead, the universe has always existed, looking roughly the same from every point and at every time, but this presented an immediate puzzle. If the universe is expanding, as observations clearly showed, then the density of matter should be constantly decreasing as galaxies drift further apart. The steady-state theory offered a breathtaking solution. It proposed that new matter is continuously being created, ex nihilo, out of nothing, at a rate so slow it is undetectable. Just a few atoms per cubic kilometer every century would be enough to fill the gaps and maintain a constant, steady density throughout an infinite and eternal cosmos. The theory's most famous champion was the brilliant and outspoken astronomer Fred Hoyle. It was Hoyle, in fact, who gave the rival theory its famous name. During a 1949 radio broadcast, he used the term Big Bang dismissively, intending to mock what he saw as an unscientific and almost theological idea of a sudden beginning. The name, of course, stuck, but not in the way he had hoped. For a time, the debate between these two models, the eternal steady state and the cataclysmic Big Bang, was the central battle in cosmology. The intellectual clash was fierce and personal. Then, in the mid-1960s, a discovery was made that would tip the scales decisively. Two radio astronomers accidentally detected a faint, uniform static coming from all directions in the sky. This was the cosmic microwave background radiation, the cooled remnant of the universe's hot, dense youth. It was the smoking gun, the precise afterglow predicted by Big Bang models, and something the eternal steady-state universe simply could not explain. With that evidence, the steady-state theory, in its original form, was essentially laid to rest, yet its story is a powerful reminder of how scientific consensus can shift dramatically with new data. And in a fascinating twist, the spirit of the idea has not completely vanished. Some modern cosmological models, seeking to explain dark energy or the nature of the vacuum, incorporate concepts of continuous creation in more subtle, mathematically complex ways. The universe may not be in a perfect steady state, but the bold idea of an ever-renewing cosmos continues to inspire physicists to question the very nature of nothingness and existence. That discovery of the cosmic microwave background seemed to seal the fate of an eternal universe, but the human imagination is not so easily contained. If a single beginning felt philosophically troubling, perhaps the answer was not one universe, but an infinite series of them. This leads us to a theory that redefines eternity, the cyclic model. It proposes that our universe is not the first and only act in the cosmic play, but merely the current scene in a drama that has been running forever. In this grand vision, the cosmos undergoes an endless cycle of expansion and contraction. We are living in the expansion phase, what we call the Big Bang. But one day, this expansion will slow, halt, and reverse. All the galaxies will rush back toward each other in a cataclysmic event known as the Big Crunch. Everything, every star, every planet, every atom would collapse back into an incredibly hot, dense state, a new singularity, but instead of being a final end, this singularity then becomes the seed for the next Big Bang, birthing a brand new universe from the ashes of the old. This cycle of bang, expansion, crunch, and rebirth is proposed to have been repeating for an infinite length of time, with no ultimate beginning and no final end. It elegantly sidesteps the perplexing question of what happened before the Big Bang, because in this model, there simply is no before, only an endless, looping procession of cosmic epochs. Each universe inherits the energy and matter of its predecessor, but is then completely reborn, its physical laws potentially reset. The mechanisms proposed for this incredible process are as mind-bending as the idea itself. One of the most compelling comes from the realm of string theory and involves entities known as brains. Imagine our entire universe, with its 3 dimensions of space, is actually a vast, floating membrane, or brain, existing within a higher dimensional space. Now picture another such brain, a parallel universe, floating nearby in this cosmic bulk. The cyclic model suggests that these brains could periodically collide. When 2 such universe-sized membranes smash into each other, the immense energy of that collision, from our perspective inside one of the brains, would look exactly like a hot, dense Big Bang. The universe expands from that collision, cools, and forms galaxies, all while the brains drift apart. Then, drawn by some fundamental force, they swing back together over trillions of years, leading to another collision and another new beginning. This brain collision model provides a potential physical driver for the cycle, turning the mysterious singularity into a consequence of a colossal, higher dimensional event. Yet, for all its elegant beauty, the cyclic model is not without fierce controversy. The biggest question is what, exactly, powers the rebound? What force overcomes the immense gravity of a big crunch to make the universe bounce back instead of just ending? Some theories propose a mysterious dark energy field that reverses its effect, pushing everything apart once the collapse reaches a critical density. Others rely on the complex mathematics of quantum gravity, suggesting the universe becomes so dense that the very rules of physics change, generating a repulsive force that triggers the next bang. The challenge is that these are largely theoretical propositions, difficult or perhaps even impossible to test directly. how could we ever find evidence of a previous universe that was utterly erased in a big crunch? Some physicists suggest subtle patterns in the cosmic microwave background might hold imprints from a pre-bang era, like faint echoes from a time before time. But for now, the cyclic model remains a powerful and haunting possibility, a vision of a cosmos that never truly dies, but is forever renewed in an infinite dance of creation and destruction. Yet the idea of a cyclic cosmos is not the only challenge to the standard story. Another theory emerges from the shadows of modern physics, one that suggests we have been looking at the universe through the wrong lens entirely. This is the plasma universe, also known as the electric universe. It is a cosmology that fundamentally reorders the forces of nature, placing electromagnetism, not gravity, as the primary architect of the cosmos. In this view, space is not an empty void, but is filled with an invisible electrified gas called plasma. This plasma is not a perfect vacuum, but a sea of charged particles, and it is threaded by vast, powerful electric currents that flow across unimaginable distances. These cosmic currents, according to the theory, are the true sculptors of the universe. They are what form galaxies, shape nebulae, and power stars, all without any need for the mysterious, unseen substance we call dark matter. The swirling arms of a spiral galaxy are not held together by the gravity of invisible halos, but by the magnetic fields generated by immense electric currents flowing through the plasma of interstellar space. A star is not merely a ball of gas powered by gravity and nuclear fusion alone, but an electric discharge, a focus of immense electrical energy drawn from the galactic circuit. This leads to a radical conclusion about our origins. The electric universe model entirely rejects the Big Bang. It posits an eternal, infinite universe with no beginning and no end, one that is constantly evolving and being reshaped by electromagnetic forces. This eternal nature is maintained through a continuous flow of electrical energy, a concept that echoes the old steady-state idea, but through a completely different physical mechanism. To achieve this, the theory makes a deeply controversial claim about one of the pillars of modern astronomy, the redshift of light. Edwin Hubble interpreted the redshift of distant galaxies as a Doppler effect, meaning they are moving away from us, which became the key evidence for an expanding universe. The electric universe proponents argue this interpretation is a fundamental mistake. They suggest that redshift is not a reliable indicator of velocity or distance, but can be caused by other, poorly understood processes, perhaps even as light loses energy while traveling through the tenuous cosmic plasma. If they are right, then the entire edifice of the expanding universe and the Big Bang collapses. The cosmic microwave background, that faint afterglow, would then have to be explained not as a relic of a primeval fireball, but as the simple thermal radiation of interstellar dust, energized by those same cosmic currents. The theory points to celestial phenomena that seem to have a difficult electrical explanation, such as the precise and filamentary structures seen in some nebulae, or the powerful radio emissions from certain galaxies, as potential proof. Yet, for all its internal consistency and passionate advocacy, the plasma universe is viewed by the vast majority of cosmologists as pseudoscience. The opposition is fierce and nearly universal. Mainstream physics argues that the theory's explanations for well-established observations, like the precise characteristics of the cosmic microwave background or the behavior of gravitational lenses, are inadequate. They point out that while electromagnetism is powerful, its force diminishes with distance far more quickly than gravity, making it difficult to see how it could orchestrate structures on the scale of galaxy clusters. The debate is not a polite academic disagreement, it is a fundamental schism over the very rules of evidence and what constitutes valid science. Proponents of the electric universe often position themselves as rebels against an entrenched and dogmatic establishment, arguing that mainstream cosmology is blinded by its own assumptions. The mainstream, in turn, sees a theory that cherry-picks anomalies while failing to provide the quantitative, predictive power that is the hallmark of robust physical models. This standoff leaves us with a critical question. Is the electric universe a revolutionary paradigm waiting for its moment, or a compelling but ultimately flawed alternative that misunderstands the fundamental nature of the cosmos? The clash between gravity and electromagnetism is a battle over which force truly rules the cosmos, but an even deeper theory questions the very nature of the space those forces operate in. What if our three-dimensional reality, with its vast depths and towering heights, is nothing more than a magnificent illusion? This is the staggering claim of the holographic principle. It suggests that our universe, in all its rich, three-dimensional glory, might actually be a holographic projection encoded on a distant, two-dimensional surface. We are, in essence, living inside a cosmic mirage. This idea did not emerge from pure speculation, but from one of the most profound puzzles in physics, the behavior of black holes. When something falls into a black hole, according to the laws of quantum mechanics, the information that describes it can never be truly destroyed, but according to general relativity, it is lost forever behind the event horizon. This is the black hole information paradox. To resolve it, physicists like Jacob Bekenstein and Stephen Hawking discovered that the maximum amount of information a region of space can contain is not proportional to its volume, as you might expect, but to the surface area of its boundary. A black hole's entropy, which is a measure of its information content, is tied to the area of its event horizon. This was a bizarre clue. It is as if all the things that happen within the three-dimensional volume of a black hole are actually encoded on its two-dimensional surface, like a DVD storing the data for a three-dimensional movie. The holographic principle takes this clue and applies it to the entire universe. In this view, the distant, two-dimensional boundary of our cosmos, a surface at the end of space and time, contains all the information needed to generate every star, every planet, and every one of us within the three-dimensional bulk. We are the projection. The mathematics behind this often comes from string theory, where certain descriptions of a universe with gravity in three dimensions can be perfectly equivalent to a quantum field theory without gravity operating on its two-dimensional boundary. This is not just a vague analogy, it is a precise mathematical duality. The implications are enough to shatter your perception of reality. If the holographic principle is correct, then the fundamental stuff of the universe may not be matter or energy, but information. The universe is a cosmic computer, and reality is the output. Your experience of moving through a spacious world is a convincing rendering, much like a character in an incredibly advanced video game believes in the world it inhabits. This leads to deeply controversial questions. How could we ever test such a thing? Some experiments have looked for evidence in the cosmic microwave background, searching for a telltale graininess or noise that would betray the pixelated nature of spacetime at the tiniest possible scale, the Planck length. So far, no such evidence has been found. Other proposals suggest that precise measurements of quantum entanglement might reveal the hidden two-dimensional code. The greatest controversy, however, is philosophical. It challenges our most basic assumptions about what is real. Are the dimensions we experience every day fundamental, or are they merely emergent properties, a convenient user interface for a deeper, flatter reality? The holographic principle does not just offer a new theory for the universe's origin, it forces us to wonder if the stage upon which the cosmic drama plays out is itself a grand and breathtaking deception. This idea of a holographic universe, where reality is a projection, leads to an even more unsettling possibility. What if our cosmos is not a natural phenomenon at all, but an artificial construction? a sophisticated simulation running on some kind of cosmic computer. This is the simulation hypothesis, a theory that has leapt from science fiction into serious philosophical and scientific debate. The modern argument was powerfully framed by the philosopher Nick Bostrom. He proposed a simple but profound trilemma, a set of three possibilities, one of which must be true. First, almost all civilizations at our level of development go extinct before they can create advanced simulations. Second, any civilization that reaches that technological maturity has no interest in running vast numbers of simulations of their own ancestors. Or third, we are almost certainly living inside a simulation right now. The logic is based on a simple projection. If a civilization ever becomes capable of creating realistic simulations of conscious beings, and if it has even a modest desire to run them, then the number of simulated minds would quickly and vastly outnumber the one base reality. Therefore, from a statistical standpoint, any randomly selected conscious being, like you or me, is far more likely to be one of the simulated ones. This argument has found surprising traction beyond philosophy. Tech entrepreneurs like Elon Musk have publicly argued that the odds we are in base reality are astronomically low, perhaps 1 in billions. Their reasoning stems from the breathtaking pace of our own technological progress. Within just over a century, we have gone from rudimentary mechanical computers to creating immersive virtual worlds. If this trend continues for just a few more centuries or millennia, our descendants would possess computing power so vast that running a simulation of an entire universe, with sentient inhabitants who believe their world is real, would be trivial for them. The scientific plausibility of the idea hinges on the very nature of reality as uncovered by modern physics. Quantum mechanics, for instance, suggests that the universe is not continuously smooth, but operates in discrete, tiny packets of energy and quantized space, much like the pixels in a digital image. The finite speed of light could be seen as a processing limit, preventing any part of the simulation from rendering information faster than the system can handle. Even the strange laws of quantum physics, where particles exist in blurred states of probability until observed, bear an uncanny resemblance to a computer program that only renders the fine details of a scene when a player is actively looking at it, a technique used in video game design to conserve processing power. Yet, the simulation hypothesis is engulfed in fierce controversy. The most fundamental criticism is whether it is even a scientific theory at all. Can it be tested? Some physicists have proposed potential experiments, like looking for glitches in the fabric of reality, or detecting shortcuts a simulating computer might take in its calculations. Others argue it is fundamentally untestable and therefore belongs to the realm of philosophy, not science. If a simulation is perfect, by definition, we would have no way to perceive the world outside it. The implications, if true, are existentially jarring. What does it mean for free will if our choices are just the output of a complex algorithm? Is consciousness itself just an emergent property of simulated neural networks? And what is the ultimate meaning of existence if our entire universe, with all its beauty and tragedy, is merely someone else's entertainment or experiment? The simulation hypothesis does not offer a comforting origin story, but it forces us to confront the very nature of our reality, questioning whether the cosmos is a fundamental truth or the ultimate artifact. The idea of a simulated reality pushes the boundaries of science, but there is another realm of thought that approaches the origin of the universe from a completely different foundation. For billions of people around the world, the cosmos did not begin with a random singularity or a collision of brains, but with a deliberate act of divine creation. These creationist cosmologies present a universe with purpose and meaning, a stark contrast to the impersonal forces of most scientific models. Among the most discussed is young Earth creationism, which interprets religious texts, like the Book of Genesis, as a literal historical record. This perspective posits that the entire universe, including our planet, was created by a supernatural being in a series of events spanning 6 days, and that the Earth itself is only a few thousand years old, often calculated to be around 6,000 years based on biblical genealogies. This immediately creates a profound conflict with established science, which measures the age of the universe at 13.8 billion years and the Earth at 4.5 billion years. To reconcile this vast discrepancy, proponents of young Earth creationism have developed a range of scientific arguments. They question the reliability of radiometric dating methods used on rocks, suggesting that decay rates may not have been constant throughout history. A major focus is the problem of starlight from distant galaxies. We can see galaxies that are billions of light years away, meaning the light has been traveling for billions of years to reach us. In a universe only thousands of years old, how could we see that light already? One proposed solution is the idea that God may have created the light already in transit, so that Adam would have seen a star-filled sky on his first night. Another suggestion is that the speed of light itself was vastly different in the past, a concept with deep and controversial implications for physics. The debate extends to geology, where the immense layers of sedimentary rock and the fossil record, interpreted by mainstream science as evidence of an ancient Earth and evolution, are instead explained by a single, global catastrophic event, the Great Flood described in the Bible. This flood, they argue, could have carved canyons, deposited continents worth of sediment, and buried the dinosaurs in a relatively short period. This leads to the most public and heated controversy, the place of these ideas in science education. For decades, there has been a persistent effort in some regions to have creationism, or its more modern iteration known as intelligent design, taught alongside evolution in public school science classrooms. Proponents argue that this represents academic freedom and the teaching of alternative theories. The overwhelming majority of the scientific community, along with numerous court rulings, strongly opposes this. Their position is based on a fundamental philosophical divide known as methodological naturalism. This is the working rule of science that limits its inquiries to natural causes and observable, testable phenomena. Science, by its very definition, cannot invoke supernatural miracles as explanations because they are not testable or falsifiable through experiment. A supernatural act, by its nature, cannot be replicated or measured in a lab. To scientists, introducing a creator into a scientific explanation is not a competing theory, it is the end of the scientific process. It replaces the search for a natural mechanism with an untestable assertion. This is why organizations like the National Academy of Sciences state unequivocally that creationism and intelligent design are not science, but religious beliefs, and have no place in a science curriculum. The conflict, therefore, is not merely about the age of a rock or the distance to a star. It is a deep, centuries-old clash between two different ways of knowing the world, one based on faith and revelation, and the other on observation, reason, and testable evidence. Both seek to answer humanity's oldest questions, but they build their answers on foundations that are, for now, irreconcilable. That philosophical chasm between faith and science is one way to question our single universe, but modern physics offers another, one that multiplies reality itself. We enter the realm of the multiverse, a hypothesis that suggests our cosmos is just one bubble in an infinite, frothing sea of universes. This is not a single idea, but a collection of related concepts emerging from the most advanced areas of theoretical physics. The first and perhaps most intuitive version comes from the theory of cosmic inflation. This suggests that the rapid expansion of the early universe never truly stopped. Instead, the fabric of spacetime continues to inflate eternally, but only in a vast background cosmos. Within this inflating background, random quantum fluctuations can cause pockets to stop inflating and pinch off, each one becoming its own separate Big Bang, its own self-contained universe. In this eternal inflation scenario, new bubble universes are being born all the time, an infinite number of them, each with its own unique properties. A second, even more mind-bending version of the multiverse arises from the strange world of quantum mechanics. According to the conventional Copenhagen interpretation, a quantum particle exists in a haze of probabilities until it is observed, at which point its wave function collapses into a single, definite state. But the many worlds interpretation proposed by Hugh Everett rejects this idea of collapse. Instead, it suggests that every time a quantum event has multiple possible outcomes, the entire universe splits into branches, each one realizing a different possibility. In this view, a version of you exists for every choice you ever made, and for every choice you did not make. There is a universe where you turned left instead of right, and another where the dinosaurs were never wiped out by an asteroid. Reality is a constantly branching tree of every possible timeline. A third version comes from the complex mathematics of string theory. This theory attempts to unify all forces and particles by describing them as tiny, vibrating strings. But for the math to work, string theory requires extra spatial dimensions, and it predicts a staggering number of possible stable configurations for those dimensions, perhaps 10 to the 500 or more. Each configuration corresponds to a universe with a different set of physical laws and constants. This is known as the string theory landscape, and our universe is just one tiny habitable plot in an impossibly vast cosmic garden of possibilities. Together, these multiverse ideas offer a radical solution to one of cosmology's greatest mysteries, the problem of fine-tuning. The fundamental constants of nature, like the strength of gravity or the mass of an electron, appear to be perfectly calibrated for the existence of life. If any of these values were even slightly different, atoms would not hold together, stars would not burn, and life could never arise. So why is our universe so hospitable? The multiverse provides a staggering answer. If there are an infinite number of universes, each with random physical laws, then it is no surprise that we find ourselves in one of the rare, finely tuned ones that can support us. We are the winners of a cosmic lottery. This, however, is the heart of a furious controversy. Is the multiverse a scientific theory, or is it a philosophical speculation disguised as physics? The core of science is testability and falsifiability. If these other universes are forever separated from us by an inflating void or a different quantum branch, how could we ever observe them? Critics argue that the multiverse is not science, but a retreat from it, an untestable idea that explains everything and therefore predicts nothing. Proponents counter that we might find indirect evidence. The shape of our own universe, or specific patterns in the cosmic microwave background, could bear the scars of a collision with another bubble universe in the distant past. They also argue that the theories that predict the multiverse, like inflation and string theory, are themselves testable in other ways, and the multiverse is a natural consequence of their math. The debate forces a difficult question. At the very frontiers of knowledge, where direct experimentation becomes impossible, what kind of evidence should we accept? Must all science be based on direct observation, or can we be convinced by the sheer logical and mathematical necessity of an idea, even if we can never visit the reality it describes? The multiverse hypothesis does not just challenge our place in the cosmos, it challenges our very definition of what science is. This statistical inevitability of our existence in a habitable cosmos is precisely what the anthropic principle seeks to formalize. It is a line of reasoning that turns the fine-tuning problem on its head. Instead of asking why the universe is so perfectly suited for life, it states that we could only ever find ourselves in a universe that is capable of supporting us. The principle comes in two distinct forms, each with profound implications. The weak anthropic principle is the simpler, almost common-sense version. It notes that the physical constants and conditions we observe in the universe must be compatible with the existence of carbon-based observers. We should not be surprised to see a universe that allows our existence, because in a universe that did not, we would not be here to be surprised. It is a cosmic version of a survivor's bias. Imagine a puddle of water waking up one morning and thinking, "This hole I am in fits me perfectly. It must have been made just for me." The puddle is noticing its local environment is suitable, but it is not questioning the broader processes that created the hole in the first place. This weak version is widely accepted, as it is a simple statement about our location in time and space within a potentially vast and varied cosmos. Then there is the far more controversial strong anthropic principle. This version asserts that the universe must have properties that allow life to develop within it at some stage in its history. The word "must" is the source of the controversy. It implies a kind of cosmic constraint, a rule that the universe is compelled to be life-friendly. This can sound eerily close to a design argument, as if the laws of physics were somehow preordained with the goal of producing observers. Proponents use this strong principle as a direct answer to fine-tuning, suggesting that the constants are what they are because life is a necessary outcome. The debate this ignites is fierce and deeply philosophical. Is the anthropic principle a genuine scientific explanation, or is it merely a trivial truism, a tautology that explains nothing? Critics argue that saying we exist because we exist is not an explanation at all. It is like saying the sky is blue because we see it as blue. It describes the situation but provides no causal mechanism. It tells us why we see fine tuning, but it says absolutely nothing about why the tuning exists in the first place. Does the principle actually solve the problem? Or does it just restate it in a way that makes us feel like we have an answer? This strikes at the very heart of what science is supposed to do. Science seeks causes, mechanisms, and testable predictions. The anthropic principle, especially in its strong form, seems to offer none of these. It is often accused of being an unscientific cop-out, a way to avoid the deeper, more challenging questions about our cosmic origins. Why do these specific laws exist? The multiverse offers one potential mechanism, a cosmic lottery. The strong anthropic principle, by itself, offers no mechanism at all. It simply posits a universe that is necessarily life-friendly, leaving the how and the why completely unanswered. The ongoing debates in the philosophy of science rage over whether this line of reasoning has any legitimate explanatory power, or if it is the point where science must simply stop and admit that some questions about ultimate reality may be beyond its reach. While the holographic principle redefines reality and the multiverse multiplies it, another theory offers a different kind of cosmic cycle, one born not from a bounce but from a collision. The ekpyrotic universe model presents a spectacular vision of creation, where our entire cosmos is the aftermath of a shattering impact between two parallel worlds. This idea emerges from the intricate mathematics of string theory, where the fundamental building blocks of reality are not particles, but tiny, vibrating strings. In this framework, our familiar three-dimensional universe could be a membrane, or brain for short, existing within a higher dimensional space. The ekpyrotic scenario proposes that another such three-dimensional brain floats parallel to our own, separated by a tiny gap in a hidden dimension. Our Big Bang was not an explosion from a point, but the result of this neighboring brain smashing into ours. The immense kinetic energy of that collision, from our perspective trapped within our brain, would have manifested as an unimaginable fireball of heat and radiation, instantly creating the hot, dense state we identify as the beginning of our universe. This model directly challenges the traditional cyclic idea of a big crunch where the universe collapses under its own gravity. Here, there is no collapse. Instead, after the collision, the two brains bounce apart, causing our universe to expand and cool. They then slowly drift back together over trillions of years, drawn by a faint force between them, setting the stage for the next cataclysmic impact and a new cosmic beginning. This process solves one of the great puzzles of the standard Big Bang, known as the horizon problem. The cosmic microwave background is almost perfectly uniform in temperature, yet regions of the sky on opposite sides are so far apart that light could never have traveled between them to equalize their temperature. Inflation theory solves this with a period of ultra-fast expansion, but the ekpyrotic model offers a different solution. Because the pre-bang state was a cold, nearly empty brain, it had ample time to settle into a uniform temperature long before the collision. The bang itself then heated this already uniform landscape, naturally explaining why we see such consistency in every direction we look. The most exciting and controversial aspect of this theory is a prediction it makes about the fabric of spacetime. The violent shearing motion of two brains scraping past each other would have sent powerful tremors through the cosmos, gravitational waves with a very distinct, non-random pattern or polarization. These primordial gravitational waves would leave a specific imprint on the cosmic microwave background. While inflation also predicts gravitational waves, the signal from an ekpyrotic collision would be significantly weaker and have a different character. This gives scientists a potential way to test the idea. If we can build sensitive enough instruments to detect this specific fingerprint in the ancient light of the cosmos, we could have definitive evidence that our universe was born from a brain collision. This very possibility lies at the heart of an ongoing and fierce debate in theoretical physics. Proponents see the ekpyrotic model as an elegant, testable alternative to inflation, one that naturally incorporates a cyclic universe without the thorny problems of a singularity. Critics, however, question whether it is genuine progress or just beautiful mathematics. They argue that the higher dimensional bulk space and the brains themselves are purely theoretical constructs with no independent evidence for their existence. The entire framework rests on the unproven foundations of string theory, which itself has been criticized for making few testable predictions. Is the ekpyrotic universe a profound insight into the true nature of cosmic genesis, or is it an elaborate and untestable story we tell ourselves to make sense of a beginning we can never truly see? The answer may be written in the faint ripples of gravity that have been traveling across the universe since the moment of its violent birth. Roger Penrose offers a different kind of cosmic cycle, one that redefines eternity not with a bang or a crunch, but with a slow, quiet fade. His conformal cyclic cosmology proposes that our universe is just one in an infinite series, where the unimaginably distant future of one becomes the hot, dense Big Bang of the next. The mechanism for this incredible transition hinges on a fundamental reshaping of our perspective. In the far, far future, after the last black hole has evaporated and the last particle has decayed, the universe will be an empty, cold sea of massless radiation. In this state, where particles have no mass and distances become meaningless, the universe loses its sense of scale. It effectively forgets how big it is. Penrose's brilliant insight was that this vast, cold, empty end state is mathematically identical to the hot, small, dense beginning of a new universe. The end of time in one cycle becomes the beginning of time in the next, in an endless, seamless chain. This theory makes a startling prediction. If our universe was born from the death of a previous one, then that prior cosmos might have left scars on our own. Penrose and his colleagues claim to have found these scars in the oldest light we can see, the cosmic microwave background. They point to unusual, circular patches of warmer temperature, which they call Hawking points. These points, they argue, are the final explosive bursts of energy from supermassive black holes that evaporated in the previous universe. The ghostly imprint of their death throes was somehow imprinted onto the very fabric of our new cosmic beginning, like a faint watermark from a reality long gone. This claim has ignited a firestorm of debate. The mainstream cosmology community remains deeply skeptical. Many researchers argue that these so-called Hawking points are nothing more than statistical artifacts, random fluctuations that are bound to appear in any large set of data. They have run their own analyses of the cosmic microwave background and found that the patterns Penrose identifies are consistent with what you would expect from pure chance. The controversy is not just about data analysis, it strikes at one of the most sacred principles in physics, the second law of thermodynamics. This law states that entropy, or disorder, always increases. It is what gives time its arrow, distinguishing the past from the future. Conformal cyclic cosmology presents a profound challenge to this. If the universe cycles forever, then the immense entropy of the previous cosmos must somehow be reset at the moment of transition into the new Big Bang. How can a universe dying in maximum disorder give birth to a new one in a state of exquisite, low entropy order? Penrose suggests that during the conformal rescaling at the crossover point, the very concept of entropy is reset. The universe, in a sense, forgets how messy it was, allowing for a fresh start. To his critics, this is not an explanation but a hand wave, a magical erasure of a fundamental physical quantity. The debate over conformal cyclic cosmology is a battle over the limits of our theories and the nature of evidence itself. Is Roger Penrose, a Nobel laureate, seeing a profound signal from a previous Aken, or is he seeing patterns in the cosmic static where none exist? His theory forces us to confront the ultimate fate of reality and whether the arrow of time itself is merely a local phenomenon, reset with each new turn of the cosmic wheel. Roger Penrose's cyclical cosmos suggests our universe emerges from the husk of a previous one, but another theory proposes a far more nested kind of origin. The black hole universe hypothesis offers a startling possibility that our entire cosmos exists within the interior of a black hole belonging to a vast, parent universe. This is not just a poetic metaphor, but a concept grounded in the strange mathematics that describe these gravitational monsters. When you cross a black hole's event horizon, the equations of general relativity suggest that space and time swap their fundamental roles. The radial direction inward becomes a kind of time, pushing everything toward the central singularity. But what if that crushing endpoint is not a final stop, but a bridge? Some solutions to Einstein's field equations hint that the interior of a black hole could be an exponentially expanding universe, a reality born from the immense gravitational collapse in another cosmos. In this view, the Big Bang singularity was not the absolute beginning of everything, but the moment of formation for a black hole in a larger, meta-universe. The incredible heat and density we associate with our cosmic dawn was simply the energy of a collapsing star or some other vast structure in that parent realm, funneled through the event horizon to become the seed of our own reality. This idea creates a stunning, fractal vision of existence. If our universe was born inside a black hole, then every black hole that forms within our own cosmos could itself contain an entire, budding universe. Each one would be a separate cosmic branch, with its own laws of physics potentially emerging from the specific conditions of its parent black hole's formation. A star collapsing into a black hole in our night sky might, from the inside, be experiencing its own dazzling Big Bang and the birth of galaxies, This concept resonates deeply with the holographic principle, which tells us that all the information describing a three-dimensional space can be encoded on its two-dimensional boundary. The event horizon of our parent black hole would be that boundary, the cosmic hard drive storing the information that projects our seemingly vast, three-dimensional existence. The universe would not just be in a black hole, it would be a black hole, its entire history and future written on the spherical shell of its ultimate perimeter. The most controversial aspect of this hypothesis is its testability. How could we ever find evidence that we are living inside a cosmic tomb? Proponents suggest looking for subtle imprints in the cosmic microwave background, specific patterns or asymmetries that could be the scars of our violent birth from a parent black hole. Others argue that the very value of the cosmological constant, the mysterious energy driving the acceleration of our universe's expansion, might be a natural consequence of this black hole origin mechanism. The scientific debate is fierce. Critics contend that this is elegant mathematics masquerading as physics, an untestable and ultimately metaphysical idea. They point out that the known physics of black hole formation does not clearly lead to the kind of homogeneous, isotropic universe we observe. The transition from a collapsing star to a new, expanding cosmos remains a speculative leap. Are we seeing a profound connection between the largest and smallest scales of reality, or are we simply telling ourselves a compelling story to escape the philosophical unease of a true beginning? The black hole universe hypothesis forces us to consider that every dark pit in the sky might not be an end, but a secret doorway to another cosmos altogether. This symmetrical vision of time shatters our most basic experience of reality. The time-symmetric universe theory proposes that the arrow of time is an illusion and that the cosmos extends in a perfect, mirror-like fashion on both sides of the Big Bang. In this view, our universe does not have a single, unique beginning. Instead, the Big Bang is a central point of maximum density and minimum size, but not a true origin. From that central point, time flows forward into what we call our future, but it also flows backward into what we would call a past. This means that the history of the universe before the Big Bang is not a mystery, but simply the temporal mirror image of the history that came after it. The expansion we see is balanced by a period of contraction on the other side. This idea directly assaults our linear understanding of cause and effect. We are conditioned to believe that causes must always precede their effects, but in a time-symmetric cosmos, this logic breaks down. An event in the forward-moving universe could be the cause of an event in the backward-moving universe, and vice versa, creating causal loops that have no definitive starting point. The foundations for this radical idea are found in the strange rules of quantum mechanics. At the microscopic level, the fundamental equations that govern particles are largely time-symmetric. They work just as well if time runs forward or backward. It is only when we zoom out to the macroscopic world, with its countless interactions, that the illusion of a one-way arrow of time emerges from the statistical tendency toward disorder. The most controversial interpretation within this framework involves antimatter. One provocative suggestion is that antimatter is not a separate substance, but rather ordinary matter moving backward in time. Imagine an electron with its negative charge traveling forward in time. From our perspective, it is just an electron, but if that same particle were moving backward in time, its reverse temporal charge would make it appear to us as its opposite, a positively charged positron. In this view, a particle and its antiparticle are the very same entity, simply observed from opposite directions in time. This would mean that when a particle and its antiparticle annihilate in a flash of energy, what we are really seeing is a single particle reversing its direction in time, making a U-turn at the intersection of existence. If this is true, It profoundly simplifies the laws of physics, but it also leads to bizarre philosophical implications. What does free will mean in a universe where the future can influence the past just as easily as the past influences the future? Are our choices truly our own, or are they predetermined by a future state that is already written, flowing backward to guide us? The nature of temporal experience itself becomes a puzzle. Why do we perceive time as a one-way flow if the underlying reality is a static, four-dimensional block where past, present, and future all equally exist? The theory offers a stunning resolution to the problem of a beginning. There is no need for a creator or a singularity emerging from nothing, because the universe simply exists in a complete, self-contained loop of time. The question of what happened before the Big Bang becomes as meaningless as asking what is north of the North Pole. We live not at the start of a story, but in the middle of an eternal, symmetrical dance where beginnings and endings are merely artifacts of our limited perception. This idea that the universe is fundamentally mathematical is not just a tool for physicists, but a startling claim about the very substance of reality. The mathematical universe hypothesis, championed by physicist Max Tegmark, pushes this notion to its ultimate limit. It proposes that our physical world is not just described by mathematics, but that it is mathematics. In this view, you, me, the stars, and the forces that bind them are not merely things that can be modeled with equations. We are the physical instantiation of a specific, self-consistent mathematical structure. Think of it like a triangle. The mathematical idea of a triangle, with its three sides and angles adding up to 180 degrees, exists in a kind of abstract realm. The mathematical universe hypothesis suggests that our cosmos is like that triangle, a complex pattern of relationships that exists because it is mathematically possible. This idea finds its roots in what the physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. It is genuinely baffling why human-invented concepts like algebra, calculus, and complex numbers should so perfectly and powerfully describe the behavior of quarks, black holes, and the expansion of space itself. It is as if we have been discovering a hidden, pre-existing code all along, not just inventing useful fictions. Tegmark's hypothesis offers a breathtakingly simple explanation for this mystery. Mathematics works so well because reality is mathematics. From this core idea emerges the most controversial extension of the theory, the level 4 multiverse. If our universe is one particular mathematical structure, then what about all the other possible structures? Tegmark argues that every mathematically consistent structure exists in just as real a physical sense as our own cosmos. There is a universe governed by the rules of chess. There is a universe where gravity is repulsive. There are realities with 27 dimensions of space, or where time flows in loops. Every conceivable cosmos, no matter how bizarre, is out there, physically real, simply because its governing equations are free of logical contradictions. This leads to profound and unsettling questions about consciousness. If we are just a bundle of mathematical relationships, then what is the nature of the self that perceives this reality? Is consciousness itself an emergent property of a sufficiently complex computational process, a subroutine running on the hardware of a mathematical universe? The hypothesis suggests that any self-aware substructure within a mathematical system would have a subjective experience, a first-person perspective. You are the universe's way of experiencing one specific part of its own vast mathematical nature. The debate surrounding this idea is as sharp as the mathematics it describes. Is this the ultimate theory of everything, a final, elegant answer that requires no further explanation for why the laws of physics are what they are, or is it a philosophical dead end? Critics argue that by claiming everything exists, the theory predicts nothing. it cannot tell us why we find ourselves in this particular mathematical structure and not another. It offers no mechanism for how an abstract mathematical form translates into the tangible, qualitative experience of the color red or the feeling of warmth. For many scientists, a theory that cannot be falsified or make unique predictions falls outside the realm of science altogether, becoming a metaphysical statement of faith in the power of mathematics. Are we uncovering the deepest secret of existence, or have we simply replaced a mysterious physical reality with an equally mysterious mathematical one? But if the universe is a mathematical structure who is doing the calculating, this question lies at the heart of one of the most mind-bending theories of all, the participatory anthropic principle proposed by the brilliant physicist John Wheeler. He took the observer effect in quantum mechanics to its most radical conclusion, suggesting that the universe only comes into a definite state when it is observed by a conscious being. In this view, we are not just passive inhabitants of a pre-existing cosmos, we are active participants who bring it into reality through the very act of looking at it. Wheeler's famous phrase captures it perfectly: it from bit, the physical universe, the it, emerges from information, the bit, and that information is only solidified when an observation is made. This turns our everyday understanding of cause and effect completely upside down. The present does not just flow from the past, the present can reach back and influence the past. This is not just philosophy, it is the stunning implication of a class of experiments known as delayed choice experiments. Imagine a single particle of light, a photon, traveling through a laboratory apparatus toward a screen with two slits. If you do not measure which slit it goes through, it behaves like a wave and passes through both simultaneously, creating an interference pattern. But if you place a detector at the slits to observe its path, it abruptly behaves like a single particle and the interference pattern vanishes. Now, Wheeler's genius was to propose a delayed choice. What if you wait until the very last possible moment, after the photon has already passed through the slits, but before it hits the final screen, to decide whether or not to measure its path? Astonishingly, the result is the same. The photon's behavior, whether it went through one slit or both, seems to be determined retroactively by the choice you make in the present. It is as if the photon's history is not fixed until you look back at it. This suggests that the universe's entire timeline remains in a fuzzy, undefined state of possibilities until a conscious observer makes a measurement, forcing one specific history to snap into place. The controversy this ignites is among the most profound in all of science. What or who qualifies as an observer? Does it require a human mind, or is a simple detector enough? If a detector can collapse a quantum wave function, then the universe could have existed for billions of years before life evolved, seemingly without any need for a conscious participant. This is the major critique from most mainstream physicists, who see Wheeler's interpretation as an unnecessary injection of mysticism into physics. They argue for interpretations like the many worlds theory, where every possibility happens in a branching reality, eliminating the need for a special role for consciousness. For them, the participatory anthropic principle is an extreme and untestable speculation, a step too far beyond the equations, yet the idea persists, forcing us to confront the deepest questions about our relationship with the cosmos. Are we merely reading the story of the universe, or are we, in some strange and fundamental way, the authors writing it as we go along? These attempts to redefine time and observation push the boundaries of physics, but a far more direct challenge to the cosmic expansion story is brewing. A small group of physicists is quietly reviving the idea of a static universe, a cosmos with no beginning and no large-scale expansion. This modern revival is fueled by growing cracks in our standard model, known as cosmological tensions. Measurements of the universe's current expansion rate, the Hubble constant, do not perfectly align when taken with different methods, creating a nagging inconsistency that some believe points to a fundamental flaw. To salvage a static cosmos, these theorists must find a way to explain the key evidence for expansion, primarily the redshift of distant galaxies. The mainstream interpretation that redshift is a Doppler effect from galaxies flying away is the bedrock of the Big Bang. The static model offers a radical alternative called the tired light theory. It proposes that light from distant stars loses energy over vast cosmic distances, not because the source is moving, but because the photons themselves grow tired. This energy loss would cause the light to shift toward the red end of the spectrum, mimicking the effect of recession. The mechanism for this energy loss is the great controversy. Some suggest it could be due to tiny, repeated interactions with the sparse particles and fields that fill the supposed void of space. Others propose it is a fundamental property of light itself, a gradual dimming we have not yet understood. If true, the universe would not be expanding, and the Big Bang would be an illusion. However, this static vision faces immense hurdles from other, more complex observations. The evidence from distant supernova is particularly damning. In the late 1990s, astronomers observed that certain types of exploding stars, standard candles whose intrinsic brightness is known, appeared fainter than expected in an expanding universe. This was the key discovery that revealed the expansion is not just happening, but accelerating, driven by the mysterious force of dark energy. A static universe simply cannot explain why these supernovae would be systematically dimmer across vast distances unless the fabric of space itself is stretching. Furthermore, the precise characteristics of the cosmic microwave background radiation present an even greater challenge. This ancient afterglow has a specific blackbody spectrum and shows subtle temperature variations that perfectly match the predictions of a hot, dense, expanding universe that has cooled over billions of years. A static, eternal cosmos would struggle to produce this specific thermal radiation and the intricate pattern of hot and cold spots that seeded the formation of galaxies. Why, then, does this small but persistent minority continue to pursue what many consider a disproven idea? Their motivation is a profound unease with the foundational pillars of modern cosmology. They argue that dark energy and dark matter, the two invisible components that make up 95% of the universe in the Standard Model, are ad hoc inventions, mysterious fudge factors needed to make the equations fit an expanding universe. By rejecting expansion itself, they seek a simpler, more elegant cosmos, one governed by modified laws of gravity or other yet to be discovered physics that can explain the observations without invoking these vast, unseen realms. It is a high-stakes gamble, a bet that our entire understanding of cosmic history is built on a misinterpretation of a red glow. The strange idea of a static universe forces us back to the most fundamental problem in all of physics, the very nature of gravity itself. To truly understand the origin of everything, we must venture into the realm of quantum gravity, where the rules of the very large and the very small collide. This is not one single theory, but a fierce competition of ideas, all aiming to solve the ultimate puzzle: what happened at the moment of the Big Bang, when the universe was smaller than an atom? The greatest minds of the 20th century gave us two pillars of physics: Einstein's general relativity, which masterfully describes the cosmos and its gravitational dance, and quantum mechanics, which governs the bizarre, probabilistic world of particles. The problem is, these two theories are fundamentally incompatible. They speak different mathematical languages and break down completely under the extreme conditions of the singularity, that point of infinite density where our cosmic story is supposed to have begun. Quantum gravity seeks to unify them, to find a single set of laws that works everywhere, and in doing so, it promises to rewrite the very first chapter of our universe. One of the most prominent contenders is loop quantum gravity. This theory proposes that space itself is not a smooth, continuous fabric, but is woven from tiny, indivisible loops, a network of intersecting threads of gravitational field. Think of the fabric of spacetime as a piece of cloth. Einstein saw it as a continuous sheet that could warp and bend. Loop quantum gravity suggests the cloth is actually made of individual, woven threads. You cannot have half a thread. Space comes in discrete, quantized units. This has a breathtaking consequence for the Big Bang. If space is quantized, it cannot be compressed into an infinitely dense point. There is a smallest possible size, so what happens when you run the cosmic film backward? Instead of a singularity, the universe contracts to this minimum size and then, driven by a powerful repulsive force generated by the quantum nature of gravity, it bounces. Our Big Bang was not a bang from nothing, but a big bounce from a previous, collapsing universe. Our entire cosmos could be the rebound from a cosmic contraction that came before. Another fascinating approach is causal set theory. This framework suggests that the fundamental building blocks of reality are not particles or fields, but simple, discrete events connected in a web of cause and effect. The continuum of space and time we experience is an illusion that emerges from this vast, underlying network of causal relationships. It is like looking at a bustling city from a great height. The smooth flow of traffic emerges from the individual decisions of millions of drivers. In this view, the Big Bang singularity is not a point in space, but the very first event in the cosmic web, the primordial cause from which all other events ultimately descend. The controversy surrounding these quantum gravity origins is as dense as the singularity they seek to replace. The mathematical foundations are extraordinarily complex and abstract, often making it difficult to connect them to the tangible universe we observe. The greatest challenge for all of them is testability. How can we possibly find evidence for a quantum bounce that occurred 13.8 billion years ago, or for the granular structure of spacetime at a scale a trillion times smaller than an atom? Some proposals suggest looking for faint imprints of a pre-bounce universe in the cosmic microwave background, or for subtle deviations in the behavior of the highest energy cosmic rays. Others hope that the next generation of gravitational wave detectors might catch a whisper from the first moments after the bounce, yet, for now, these remain hopeful speculations. The competition between loop quantum gravity, string theory, causal set theory, and other approaches is a battle for the soul of physics. Each camp believes its path is the most elegant, the most natural way to unify reality. This is not just an academic debate, it is a struggle to answer the most profound question we can ask: how did everything, from the vastest galaxy to the smallest particle, first come to be? These quantum gravity theories force us to question the very stage upon which reality performs. What if space and time themselves are not the foundation of the cosmos, but merely the show? This is the radical proposition of the emergent universe scenario. It suggests that the three dimensions of space and the one dimension of time we experience are not fundamental. They are not the starting point of creation, but rather properties that emerge from a deeper, more primitive layer of reality, much like the smooth surface of a lake emerges from the chaotic dance of countless water molecules. In this view, the universe did not begin within space and time, but space and time began within the universe. They are the result, not the cause, so what is this deeper layer? Different theories point to different candidates, but they often converge on the concept of information. The fundamental stuff of reality might not be tiny vibrating strings or loops of gravity, but bits of data, pure yes or no answers, existing in a vast, interwoven network. From the complex relationships and interactions between these bits, the familiar concepts of location, distance, and duration somehow materialize. Think of a three-dimensional graphic on a computer screen. The image has depth and perspective, but the computer's reality is just a two-dimensional grid of pixels and the electrical currents that define them. Our experience of a spacious, temporal world could be a similar kind of illusion, a user-friendly interface generated by an underlying quantum computer we have not yet learned to see. This idea has profound and controversial implications for the origin of everything. If space-time is emergent, then the Big Bang was not an explosion in a pre-existing void. It was the moment when the cosmic operating system booted up, when the first fundamental relationships between quantum bits established themselves, giving rise to the very concepts of before and after, here and there, for the very first time. The initial singularity would not be a point in space, but a boundary where our familiar notions of physics simply ceased to be applicable because the framework of spacetime had not yet emerged. This perspective creates a powerful bridge to other theories we have explored. The holographic principle is a perfect example of emergence, where a three-dimensional universe is encoded on a two-dimensional surface. The connections to quantum gravity are equally deep, as theories like loop quantum gravity and causal set theory both describe a pre-geometric reality, a world before space and time, built from discrete loops or causal events. The greatest controversy here is not just scientific, but deeply philosophical. It challenges our most basic intuition that we live in a world of objects located in a container of space, moving forward through a river of time. If emergence is correct, then this entire world view is a convenient fiction. Your feeling of moving through a room is a powerful illusion generated by the updating of relationships in a quantum network. The flow of time may not be a fundamental feature of the cosmos, but a thermodynamic artifact, a consequence of the increasing complexity of these relationships. How could we ever test such a mind-bending idea? Physicists are searching for signatures of this underlying granularity. They are looking for evidence that spacetime is pixelated at the tiniest possible scale, the Planck length. One way might be to study the highest energy light from distant gamma-ray bursts. If spacetime is a smooth continuum, all light waves should travel at the same speed. But if it is made of discrete bits, then higher energy waves might travel very slightly slower, like a large truck navigating a cobblestone road. So far, no such effect has been found, but the search continues. The emergent universe scenario does not just offer another origin story, it demands a complete redefinition of what we mean by reality, suggesting that the stage itself is the most magnificent performance of all. This fine-tuning of the universe for life is so precise it has spawned one of the most contentious modern theories, intelligent design cosmology. The argument is not based on ancient texts, but on the hard data of physics itself. It points to the fundamental constants of nature, the numerical values that govern the strength of gravity, the force binding atoms, and the mass of an electron. These values are not predicted by any known theory, they are seemingly arbitrary, and yet if any one of them were altered by even a fraction of a percent, the universe would be utterly sterile. If the force of gravity were slightly stronger, all stars would be blue giants, burning out in a few million years, far too quickly for life to evolve. If it were slightly weaker, only red dwarfs would form, unable to produce the heavy elements like carbon and oxygen that are the building blocks of planets and people. The cosmological constant, which drives the universe's expansion, is fine-tuned to an even more astonishing degree. A value just a little larger would have blown matter apart before galaxies could ever form. A little smaller and the cosmos would have collapsed back on itself shortly after the Big Bang. The odds of all these constants randomly aligning in a life-permitting configuration are often described as being like winning the lottery every single week for 1,000,000 years. Proponents of intelligent design argue that this incredible improbability is best explained by the action of a cosmic designer, an intelligence that set the dials of the universe to precisely the right values for a specific purpose, the emergence of conscious life. The scientific community, however, has offered powerful counter-arguments. The primary response is the anthropic principle, which we explored earlier. It states that we should not be surprised to find ourselves in a habitable universe, because in an uninhabitable one, we would not exist to be surprised. It is a form of observational selection bias. Another major scientific rebuttal is the multiverse. If our universe is just one of an infinite number, each with different physical laws, then it is statistically inevitable that at least one universe would have the right conditions for life. We just happen to live in that one. In this view, there is no need for a designer. We are simply the lucky winners of a cosmic lottery. This leads directly to the core of the controversy. Is intelligent design a legitimate scientific theory or a religious concept in disguise? Supporters argue it is a scientific inference based on empirical evidence, the fine-tuning itself, and that it posits a cause, intelligence, which we know from experience is capable of producing complex, information-rich structures. They contend that science should follow the evidence wherever it leads, even if it points beyond purely naturalistic causes. The overwhelming majority of scientists and scientific organizations strongly disagree. They maintain that intelligent design is not science because it is not testable or falsifiable. How could you design an experiment to detect or measure a cosmic designer? What prediction does the theory make that could be proven wrong? Critics argue that by invoking an unobservable, supernatural intelligence, the theory effectively places itself outside the realm of scientific inquiry. It is seen as a modern iteration of the God of the Gaps argument, using a current mystery in science as proof of divine action, a gap that may one day be closed by a natural explanation. The debate over intelligent design therefore rages not in laboratories, but in the overlapping territories of philosophy, public education, and the very definition of science itself. It forces a fundamental question: can a universe that appears designed be explained by unguided natural processes alone, or does the evidence point toward a deeper purpose woven into the fabric of reality? The sheer improbability of our finely tuned existence leads to one of the most unsettling paradoxes in all of cosmology. What if you, your memories, and the entire world you perceive are not the product of billions of years of cosmic evolution, but merely a fleeting, random accident? This is the Boltzmann brain paradox, a thought experiment that emerges directly from the laws of thermodynamics. It is named for the physicist Ludwig Boltzmann, who first grappled with the statistical nature of entropy, the measure of disorder. In an infinitely old or eternally inflating universe, random quantum fluctuations will eventually produce any possible configuration of matter, no matter how improbable. Given enough time, the chaotic dance of particles could spontaneously assemble a fully formed, self-aware brain, complete with fabricated memories of a past that never happened and a sensory experience of a world that does not exist. The paradox arises when we consider the probabilities. A single, disembodied brain formed by a random fluctuation is astronomically more likely to pop into existence than an entire, ordered universe spanning billions of light years with billions of galaxies and a coherent history. The math seems to suggest that in a vast and eternal cosmos, there should be vastly more of these lonely, self-aware fluctuations than there are evolved beings like us living in a real, ancient universe. This creates a devastating problem for cosmological models that predict an eternal future. such as a universe ending in heat death or one undergoing eternal inflation. If such a cosmos exists for an infinite duration, then Boltzmann brains would eventually outnumber ordinary observers like us by an infinite margin. Therefore, if our cosmological theories are correct, you are statistically almost certain to be a Boltzmann brain, a momentary flicker of consciousness soon to dissolve back into the chaos. The implications are existentially terrifying. How could you ever trust your senses, your memory of reading this sentence, your knowledge of science, your very sense of self, could all be an elaborate illusion generated by a random event that occurred a nanosecond ago? This paradox forces physicists to confront a profound question about our models of reality. Is our understanding of the cosmos fundamentally flawed if its most logical extrapolation leads to the conclusion that we are probably phantoms? The controversy has sparked intense debate, with some proposing that the universe must have a finite lifetime to avoid this absurd conclusion, while others search for a deeper principle that prevents such fluctuations from ever occurring. The Boltzmann brain paradox does not offer a comforting origin story. Instead, it serves as a stark warning that our journey to understand the cosmos might lead us to question the very reality of our own minds. The unsettling paradox of Boltzmann brains forces us to question the very nature of our reality, but what if the solution lies in a perfect mirror of our own cosmos? From the elegant mathematics of quantum field theory emerges a concept as beautiful as it is bizarre, the idea of a mirror universe. This is not a parallel realm in space, but a cosmic twin born from the fundamental symmetries of physics. The laws of our universe appear to respect three core symmetries: charge conjugation, which reverses the charge of a particle; parity, which creates its mirror image; and time reversal, which runs the clock backward. For decades, physicists believed the combined operation of all three, known as CPT symmetry, was an unbreakable law of nature. This means that if you take any physical process, flip the charges of every particle, view it in a mirror, and run it backward in time, the resulting process must be just as valid and obey the same physical laws. This profound symmetry leads to a staggering possibility. If you apply a full CPT transformation to our entire universe, you would get a valid universe that has opposite charges, is spatially mirrored, and runs backward in time. The mirror universe theory takes this idea literally. It proposes that this CPT transformed universe is not just a mathematical exercise, but a real, physical cosmos. This mirror twin would have its Big Bang where our universe has its ultimate end, and its arrow of time would point backward from our perspective. From the moment of our Big Bang, two universes were born, one moving forward in time, which is ours, and one moving backward, the mirror. This leads to a revolutionary and deeply controversial interpretation of one of the greatest mysteries in physics, the matter-antimatter asymmetry. Our universe is made almost entirely of matter, with very little antimatter, a fact that has puzzled scientists for generations. If the Big Bang created equal amounts of both, where did all the antimatter go? The mirror universe offers a breathtaking answer. What we call antimatter might not be a separate substance at all. It could simply be ordinary matter from the mirror universe, occasionally interacting with our own. In this view, a positron is not the antiparticle of an electron, it is just an electron from the mirror cosmos, whose backward-in-time nature makes it appear to us as an opposite. The matter-antimatter asymmetry is not a puzzle to be solved in our universe alone, because the antimatter is not missing. It is all residing in the mirror universe, which is made predominantly of what we would classify as antimatter. The implications are enough to warp your sense of reality. This theory suggests that the moment of creation was not a single event, but a perfectly symmetrical bifurcation, a cosmic fork in the road of time. Every event in our history has a corresponding, mirrored event in the other universe. The debate surrounding this idea is fierce and fundamental. Is the mirror universe a real physical entity, or is it merely a useful mathematical artifact, a ghost in the equations with no tangible reality? Critics argue that the CPT theorem only demands that such a universe is possible, not that it must physically exist. They see the interpretation as a step too far, a flight of fancy that cannot be tested. How could we ever observe a universe whose entire timeline runs backward and is forever separated from us by the singular moment of the Big Bang? Proponents, however, search for indirect evidence. They suggest that certain properties of neutrinos, those elusive ghost particles, or subtle violations of other symmetries, might one day provide a window into this cosmic looking glass. The theory forces us to confront a profound philosophical question: is our forward-moving experience of time an absolute truth, or is it merely a local condition, with an entire universe of time, reversed history unfolding in a direction we can never point toward? This audacious idea suggests the ultimate free lunch, a universe that came from nothing at all. The null universe hypothesis proposes that the total energy of our cosmos is precisely zero. All the positive energy bound up in stars, planets, and our own bodies is perfectly cancelled out by a vast negative energy store, the gravitational potential energy of the entire cosmos. Think of it like a cosmic bank account. Every bit of mass, every joule of radiant energy is a deposit of positive energy, but gravity, which is always attractive, acts like a universal debt. The energy you would need to pull every galaxy, every star, infinitely far apart from each other against their mutual gravitational attraction, represents a colossal negative balance. According to this theory, when you add it all up, the books balance perfectly at zero. This leads to the most staggering implication of all. If the universe truly has zero net energy, then it could have popped into existence from a perfect vacuum, from nothing, without violating the sacred law of energy conservation. You cannot create energy from nothing, but if the total is zero, you are not creating anything, you are just rearranging a zero into positive and negative parts. The quantum mechanical foundation for this lies in the bizarre behavior of the subatomic world, where virtual particles constantly flicker in and out of existence, borrowing energy from the void for fleeting moments. On a cosmic scale, the universe itself could be the ultimate quantum fluctuation, a fluctuation in the very fabric of space-time that simply never switched off. This ignites a fierce debate about the nature of nothingness. What do physicists even mean by nothing? Is it an absolute void, a complete absence of space, time, and physical law? Or is it the quantum vacuum, a seething, energetic foam pregnant with potential, which is very much something? If the universe emerged from this quantum vacuum, then it did not come from true nothingness, but from a pre-existing physical state governed by quantum laws. The controversy cuts to the heart of physics and philosophy. Can science ever explain the transition from absolute non-existence to existence, or is that a question that lies forever beyond its reach? The null universe hypothesis offers a breathtakingly elegant answer to humanity's oldest question: why is there something rather than nothing? It suggests that nothing is inherently unstable and that something, in the grandest possible sense, is the most natural state of all. That elegant balance of a zero-energy cosmos suggests a universe built on pure information. This leads us to a theory where the fundamental stuff of reality is not matter or energy, but bits. The idea of a computational universe proposes that the cosmos is, at its heart, a vast computer. It is not necessarily a simulation running on someone else's machine, but a system that is fundamentally computational in its very operation. The laws of physics are not just equations we write down, they are the algorithms the universe is running. This perspective has deep roots in the work of pioneers like Konrad Zuse, a computer scientist who speculated that the universe might be a giant digital computer, and Edward Fredkin, who argued that the most basic level of reality is a cellular automaton. Imagine a cosmic chessboard that extends throughout space and time. Each square on this board can be in one of a few simple states, like on or off. A set of simple rules dictates how each square updates its state based on the states of its neighbors. From this incredibly basic, pixelated foundation, all the complexity of the universe, from swirling galaxies to conscious thought, could emerge. The intricate dance of particles and forces we observe would be the high-level outcome of countless tiny computations happening at the smallest possible scale, the Planck length. This concept finds a powerful echo in quantum mechanics, the strange, probabilistic behavior of particles, where they exist in multiple states at once until measured, looks remarkably like a quantum computer processing a superposition of possibilities. In this view, the universe is not just like a computer, it is a quantum computer, and every interaction is a step in a cosmic calculation. The controversial claim at the core of this idea is that information is not just a description of reality, it is reality itself. A particle's mass, its charge, its spin, these are not primary qualities, they are just the information that the universe is processing about that particle. The famous equation E=mc² might be secondary to a deeper truth, that both energy and matter are manifestations of information. This forces a profound debate. Is digital physics a fundamental insight into the nature of existence, or is it just a useful metaphor, a modern way of talking about laws we do not yet fully understand? Proponents argue it resolves deep puzzles, like the black hole information paradox, by stating that information can never be destroyed, only transformed. They believe we are discovering that the universe is literally made of math and computation. Critics push back fiercely, arguing that the universe shows no clear sign of being discrete or digital. They point out that our most fundamental theories, like quantum field theory, rely on smooth, continuous fields, not pixels, the continuous spectrum of light, the smooth fabric of spacetime in general relativity. These seem to contradict a blocky, digital reality. The computational model, they say, is a powerful tool for modeling complex systems, but mistaking the map for the territory is a philosophical error. The real controversy is whether we are uncovering the ultimate programming language of the cosmos, or simply building better and better compilers for a reality whose source code we may never truly see. Yet this digital cosmos still requires an observer to give it meaning, a conscious mind to perceive the output. This leads to one of the most personally radical theories of all, the biocentric universe proposed by scientist Robert Lanza. He turns the entire relationship between life and the cosmos on its head. The conventional view is that the universe, a collection of random physical processes, eventually produced consciousness as a late and accidental byproduct. Lanza argues the opposite is true. Consciousness is not an emergent property of the brain, but a fundamental force of nature, and it is consciousness itself that creates the universe. Without a perceiver, he suggests, reality does not exist in a definite state. This idea finds a powerful, if controversial, anchor in the observer effect from quantum mechanics. You will recall the strange case of the double-slit experiment, where a particle's behavior changes depending on whether it is being watched. In Lanza's biocentric view, this is not a mere curiosity of tiny particles, it is the fundamental principle of all reality. The particle does not exist here or there until a conscious mind forces the probability wave to collapse. He extends this logic to the very fabric of space and time. We think of them as external, physical realities, but Lanza argues they are actually the tools our consciousness uses to process and make sense of the world. Time feels linear because our mind processes information in a sequential way, creating a narrative of past, present, and future from a vast array of possibilities. Space feels three-dimensional because that is the mental framework that allows us to navigate and interact with the world. In essence, life is not a passenger in the universe, it is the driver. The starry sky does not exist independently out there, it is brought into being by your act of observing it. The implications are dizzying. Death, in this model, becomes an illusion. If consciousness is primary and creates space and time, then when the body dies, that particular frame of reference ends, but consciousness itself persists outside of those constructs. The scientific community's response to biocentrism has been overwhelmingly skeptical, often dismissive. Mainstream physicists argue that Lanza has taken a specific interpretation of quantum mechanics and stretched it far beyond its logical limits. They point out that in quantum physics, an observer does not need to be conscious. A simple photographic plate or detector can collapse a wave function. To them, invoking a mysterious, fundamental consciousness is unnecessary and unscientific, a step back into mysticism. It replaces the hard problem of consciousness with an even harder problem of a cosmic mind. Why, then, does this theory persist and attract such passionate interest? It resonates because it offers something most scientific origin stories pointedly avoid: a central role for us. In a cosmos of cold equations and random chance, biocentrism places life and mind back at the very center of existence. It dares to suggest that our inner world is not just a fluke, but the very reason the outer world has any substance at all. But what if the steady march of time, the very current that carries us from birth to death, is not a fundamental river at all? The thermal time hypothesis proposes a startling idea that time is an illusion, a side effect of the universe's innate tendency toward disorder. Our deep-seated feeling that the past is fixed and the future is open may be a kind of collective mirage born from thermodynamics, the arrow of time. The reason an egg scrambles but never unscrambles itself is tied to the concept of entropy, which is a measure of randomness or chaos in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases, and this gives us a clear direction from order to disorder. This is why we remember the past but not the future. The thermal time hypothesis takes this a step further. It suggests that the flow of time itself is not a primary feature of the cosmos, but emerges from this statistical tendency. The clock you watch is not measuring some fundamental temporal substance. It is tracking the progression of the universe from a state of lower entropy to higher entropy. Your own consciousness, processing information in a brain that is itself a thermodynamic system, is swept along by this entropic current, creating the unshakable sensation of a flowing now. This leads to a profound and controversial implication. At the most fundamental level, where the basic laws of physics operate, time might not exist at all. The fundamental equations of quantum mechanics and general relativity are largely time-symmetric. They work just as well running forward or backward. The thermal time hypothesis argues that the time we experience is not in those equations because it is not fundamental. It is a collective phenomenon that appears when you have a large, complex system moving from order to disorder. This idea offers a potential solution to one of the most stubborn problems in modern physics, the problem of time in quantum gravity. When physicists try to merge general relativity with quantum mechanics, time often becomes a troublesome variable that simply vanishes from the core equations. This is deeply puzzling. How can we have a theory of everything that has no place for time? The thermal time hypothesis provides a possible answer. Time does not need to be in the fundamental equations because it is not fundamental. It emerges later as a thermodynamic property when the universe grows large and complex enough for entropy to take hold. The controversy surrounding this idea is as heated as the concept itself. If time is not real, then what are we? Are our lives, our histories, and our memories just a fleeting pattern in a timeless, static block of reality? Ongoing research explores how this thermal time might be derived from first principles and whether it can be consistently applied to the entire cosmos. The debate forces us to confront a staggering possibility that the most intimate part of our experience, the relentless tick of the clock, may be the universe's most convincing and elegant trick. We have journeyed through a dizzying array of cosmic possibilities, from a singular bang to an eternal cycle, from a holographic projection to a conscious creation. This incredible diversity of thought is not a sign of scientific failure, but a testament to the profound mystery at the heart of existence. Each theory reflects a different priority, a different philosophical stance on what constitutes a satisfying answer. Some seek to eliminate the need for a beginning entirely, while others embrace a moment of genesis. Some prioritize mathematical elegance, while others demand a central role for the observer. These controversies reveal that scientific progress is not a straight line toward a single truth, but a vibrant, often chaotic, conversation at the very edge of human knowledge. It is a process of asking better and better questions, even when the answers remain just out of reach. So where does this leave you, the observer of this grand debate? Which of these visions feels the most compelling, and more importantly, why does it resonate with you? Does the cold elegance of a mathematical multiverse satisfy your curiosity, or does the intimate role of consciousness in a biocentric cosmos feel more true to your experience? Perhaps you find the stark beauty of a universe from nothing to be the most powerful idea of all. Your personal conclusion is part of the story. The greatest discovery may not be a final answer, but the realization that the universe is far stranger and more wonderful than we ever imagined. As new telescopes peer deeper into space and new experiments probe the nature of reality, what long-held assumption about our origins might we be forced to abandon next? The conversation is far from over, and your perspective is a valuable part of it. Share your thoughts in the comments below on which theory challenges you the most. Subscribe for more journeys to the edge of understanding, and keep looking up at the stars, wondering what secrets they still hold.